Good afternoon. So I'm going to talk about the detectors. Basically, I'm going to talk about the characterization of transient noise in the advanced LIGO detectors during the event. So before any analysis on the data is done, before matching it with any template and looking or trying to get science out of this, you have to ensure that the data that is used for the analysis is quality data. So this raises a very important question of how do we know that GW 150914 was not caused by noise? In order to do that, we need to answer three important questions of what is the detector sensitive to? What are the frequencies in which it operates? And then what are all the things that can make it go wrong? What are all the possible noise sources? And then how do we deal with them? How do we deal with these sources which give noise? So here is a picture of the detectors. This is LIGO Hanford on the left in Washington, and this is LIGO Livingston in Louisiana on the right. So let's talk about the detector sensitivity. Now, ideally, gravitational wave signals are from a few hertz to a few kilohertz. And that is the frequency range in which we want the noise to be least. Essentially, the detectors are designed in a way that for extremely high and extremely low frequencies, the noise is comparatively higher. And there's a sweet spot between 30 to 500 hertz in which the noise is minimal. What this means is that the noise is almost as less loud as the signal. It's no more louder than the signal. So you're able to discern the signal if it ever comes into picture. And these individual spikes that you see, these sudden high noise spikes that you see, are because of certain sources such as mechanical stability systems and the electrical mains power supply. For example, here is a ham counterweight system which does the job of giving mechanical stability to the suspended mirrors. Then what are all the possible noise sources? To name a few, there are anthropogenic sources, basically sources which are related to human activity, such as a lab technician walking in a lab facility nearby, or a runner going for a morning jog, or a car zooming past. All of these can create disturbances loud enough that they can affect the detector sensitivity. And there are other sources such as seismic activities, earthquakes, or sea waves hitting the coast of Washington or Louisiana. These sea waves then perturb the ground, and this perturbation of the ground can sometimes be so loud that it can render the detector inoperable. And sometimes there are blips. There are certain noise events whose origins we do not know. They're simply there in the data, and there are ways to remove it. There are ways to deal with them. So how do you deal with noise sources? You come up with what is known as a veto mechanism. A veto mechanism is essentially a scheme to remove bad data. What you do is, for example, if you know that a certain component of the detector has failed at a certain point of time, the data that was collected during that time is not used in the analysis. Then there are other mechanisms such as a certain noise channel. You may know the coupling of that noise channel into the detector. If this coupling is known, then whenever such loud events happen in the noise channels, you can safely be, you can make a safe assumption that this noise has also appeared in the detector, and then you can, remove it from your data. And then there are other veto techniques which involve sources whose coupling into the detectors we do not know. For such cases, there are algorithms and schemes that have come up, which try to establish certain statistical relationships between loud events in the detector and loud events in auxiliary channels. Once these links are established, that data is removed. So essentially, the job is to remove or identify that data which you know is bad. And then there are other possible noise sources such as solar wind, the magnetic field of the sun, then radio frequency disturbances from telecom towers around. And then there is terrestrial lightning, and then there is cosmic ray showers. But it has been observed that none of these sources produce noise events loud enough that they largely affect the detector at all. So to conclude, GW150914, which was the gravitational wave detection, occurred on September 14th, 2015 at 3:21 p.m. IST. This was sometime early in the morning in Livingston and Hanford. And the data was collected to get an estimate of the background, the data was collected over a period of 39 calendar days from September 12th, 2015 to October 28th, 2015. Out of these 39 days, the Livingston and Hanford detectors were both operating at the same time for a sum total of 18 days, out of which, after performing data quality checks that I mentioned a moment ago, 16 days, effectively 16 days worth of data remained, which was then further used for the analysis. And the detectors were in perfect operational state during the event. And the vetoed out segments, the data, after the data quality, the vetoed out segments did not include the time of GW150914. And then there were other noise events which were in and around roughly the time of the event, but they were identified to be either not too loud to have caused this event in the detector, or they were in a completely different frequency range. So we can say with a really high amount of confidence that GW1509 was indeed a gravitational wave signal. And now Chandra will talk about the schemes that were used to analyze this data and perform the checks. Okay. The what?
Thanks, Sudarshan. Hello, everyone. I'll be talking about the search strategies which were used to detect the event we know as GW150914. So let me begin by reminding you what was already said in Ajith's presentation this morning, that on September 2015, so September 14, 2015, the two LIGO detectors were in data taking mode, and an online burst pipeline reported a detection of a transient signal merely 3 minutes after these events were registered in both the LIGO detectors, which happened around 9:45 GMT or around 3:50 p.m. Indian Standard Time. Now, within a few hours, another search pipeline, which we call OLIB, independently confirmed this detection, enhancing our confidence that indeed we have something very interesting in the data. Now, over coming few months, this data was thoroughly analyzed by some offline searches, and basically two completely different kind of searches were performed for this analysis. Before I go into some of the details of these pipelines, let me again remind you of the main conclusions that these searches have. So as Sudarshan mentioned, that basically we collected data for 39 calendar days, out of which 18 days we found a coincident observation time for both the detectors, and after removing the bad quality data, we ended up having 16 days of coincident data from the two LIGO detectors. And based on the analysis of data, it was found that whatever online searches found is actually an astrophysical signal coming from a coalescence of a binary black hole system, and this trigger was then called GW150914. Now, these plots have already been shown, so I just want to emphasize here that you can see this event, how rare it is as compared to the background noise. And if you see the numbers, this detection is of more than, this detection is a significance of more than 5.1 sigma, which translates into this number, which is the probability that it can be a noise is extremely small, that the false alarm rate will be just 1 in 200,000 years. The other search pipelines also did the analysis and found the signal with a significance with a more than 4.6 sigma, equivalent to a false alarm rate of 1 in 22,000 years. Now, let me go and explain one of the search pipelines in some detail. So this is the binary coalescence search pipeline, which detected the signal with 5.1 sigma. And one of the features of this pipeline is it basically performs a well-known data analysis technique in physics and astronomy. It's called match filtering to detect these gravitational wave signals. Now, I have a cartoon here displaying how this is done. So in the middle panel, what I have is a data, it's a Gaussian noise, where we have injected this signal. But of course, the noise is overwhelmingly large, and we will not be able to see it in the data. And this is a typical situation at the output of the detectors. However, this technique suggests that if you have very accurate predictions of the signal, and if you cross-correlate this with the data, then actually what you would see is this spike when the template here matches the signal which is buried into this noise. And this is how this works. However, the problem is we don't know what are the parameters of the source. And hence, we have to do some brute force analysis. We have to basically construct a bank of template. So for example, for this search, the template bank which was constructed consisted of 250,000 waveforms. And the same template bank was used for both the pipelines which were used for this analysis. Just to point out, each dot here you see represents one template, whereas the circle you see here on the top represents the template which gave the maximum signal to noise ratio in the searches. Okay, so moving ahead to the other pipeline. So unlike the previous pipeline, which is very sensitive to the information about the waveform, we need to know the waveform a priori. This pipeline basically is not very sensitive to the information of the waveform. It basically has a minimum assumptions of the signal, and then it performs the search based on, it tries to see the excess power in the data. And this plot also was shown in the morning, but what I want to show here, basically the middle panels, if you see here, there is a comparison of the reconstructed waveforms, both from generic transient search and from the previous search I mentioned, and it is compared to the numerical relativity waveforms. And what we find is an excellent agreement between these three. Finally, to summarize, we detected a gravitational wave event which is consistent with the observation of an in-spiral merger and ring down of a system of two black holes by two independent searches. These waveforms were reconstructed using the best fit models parameters and show an agreement, excellent agreement with the numerical relativity simulations. And finally, as you can see in the bottom panel, before the two objects merge, they reach the velocities of 60% of the speed of light. So it's a highly relativistic system which can basically be used for testing the predictions of the theory in the strong field regime. And we will hear more about in Abhirup's presentation. Thank you.
Actually, yeah, forgot. If you have questions, feel free to ask.
You use two kinds of techniques. One is based on a template and the other on the transient signal. So my question is, suppose you had a signal in the transient channel, but not in the template. because it so happened that it didn't fit GR. Would you have, for say this particular event, would you have the sensitivity to be able to detect it over the noise if you just had it firing in one and not in the other channel?
So basically the template-based search is more sensitive, or like more, we are more confident about this search than the burst searches. And we were lucky enough that it was a heavy system that like it produced a very significant signal in the burst search as well. So definitely we are going to pick it from the template-based searches, but like since it was a very strong signal, lasting very short duration, we also detected it in the burst.
I understand, but what I'm getting at is this. Suppose there are events in the universe which don't agree with GR, then they won't show up in your template-based channel.
Yes, of course, but
But
not
they would
for this
only
event.
show up in the second one.
Sure.
And then would you have the sensitivity to pick them out? That's what I'm trying to ask. If they only showed up in your transient search, but not in the template, would you be able to, and the rough strength is of this particular event.
Yeah, if it is very different from GR, I mean, if GR is not correct at all, then of course, like the burst searches will detect it, but like may not be GR, because like the burst searches do not know what the signal will look like. So they can detect if there is an energy, but like the template-based search will fail there. Yeah, but only if it is very different from GR.
So we have estimated, reasonable types of deviation from GR that obeys constraints from solar system, etc. Most of these will be picked up by even GR templates with a moderate loss of signal to noise ratio. So you might still be able to pick them up using template-based search unless the deviation is completely crazy. But we'll be really then worried about how to estimate parameters, or how to figure out parameters, etc. Any further questions? Okay, thank you. Off to Abhirup, Archishman.
Much of what I wanted to say has, and much of what I wanted to show has already been said by people including Rajesh and Ajith. And I, in particular, wanted to emphasize on the ICTS contribution to parameter estimation, and that part has also been taken care of by Arun. So I'm not left with much to do. However, there were some interesting questions that were asked after the presentations. My talk will hopefully answer some of those questions. We know that the signal that we observed is not a noise. It is an actual signal. We learned that in the first talk. In the second talk, we learned that it is a signal that is coming from a binary black hole merger. What next? We want to estimate, we would then like to know more about this binary black hole merger. We would like to know where this merger has taken place, what exact objects have merged. So we need to estimate the parameters of this merger. What are the parameters? As I just mentioned, they are the masses of the components that merged, their spin angular momenta, their distance to us, their location in the sky, their orientation with respect to us. Estimation of these parameters is crucial to do any further physics or astrophysics. In order to talk about the formation scenarios, in order to talk about rates, one has to know the masses. In order to see whether this theory is consistent with the fundamental physics, one has to estimate various other quantities, and some of this will be covered in subsequent talks by Arun and Abhirup. Now, when we report the parameters like the masses, we do not report a single number. Of course, we do not report a single number. We report a number with error bars. So the mass of the primary black hole could be 36, but solar masses, but it could also be 5 more than 36 or 4 less than 36. Similarly, it could be 29 plus 4 minus 4. However, how much information does this contain? Just 3 numbers. Maybe we can provide more information than that. So we provide the entire probability distribution in the space of masses. So this tells us this histogram tells us that the primary black hole mass is expected to have a peak near 35. The secondary black hole mass is expected to have a peak near 30 solar masses. And these two lines tell us, the area between these two lines is 90% of the total area. That means that in 90% of the times, the primary with 90% confidence, we can say that the primary mass is between 32 and 41. Similarly, there are these 2D histograms with the 90% and the 50% contours here. This tells us that with 50% confidence, we can say that these two masses were in this region, these two masses are in, with 90% confidence, we can say these two masses are within this region. These kinds of plots also let us study the correlations between various parameters, which are going to turn out to be important in the next few slides. One important parameter, again, this has been stated by, reported by people before me. The distance to this object is 410 megaparsecs. Again, megaparsecs is a unit that astronomers love. This megaparsec, 410 megaparsecs turns out to be 1.3 billion light years. I used to say 1.3 billion light years, but from now on I'll go and say the distance to this object is 1.3 billion gravitational wave years. Gravitational waves are expected to travel at the speed of light. In this plot, we see a very interesting degeneracy. In this plot, we see a very interesting degeneracy. The distance is not very well estimated. This is what Pratik was asking in one of after Arun's talk. And the reason the distance is not well estimated is because of the degeneracy between distance and inclination. If a source is farther away but is tilted towards us, because the leading order radiation is sort of perpendicular to the orientation plane. If the source is farther away but is tilted away from us, if the source is close together but tilted away from us, or if it is farther away but face on, they give us the same amplitude. So it's very difficult to distinguish between the two. In this context, I'd like to mention that if one includes higher modes in modeling the waveform, then one can actually break this degeneracy and come up with better estimates. And some leading effort is going on in the ICTS group, mainly by Chandra, to come up with waveforms with higher modes that can help us better estimate the distance and the inclination. Again, people have talked about the location of the event in the sky. It's located to be a patch that's 600 square degrees. 600 square degrees is 3,000 times the size of the full moon in the sky, somewhere in the southern hemisphere. These sky location is going to have implication to follow up searches that Nathan is going to talk about. There are a host of other parameters we measure, and again there was a question from Pratik about black hole spins. So one parameter we are not able to measure very well is the spin of the component black holes that merge. We can only lay some upper bounds on the maximum possible spin of the primary black hole, and this is the number. We can say that the heavier black hole was not extremal. It had at least 0.6. It had at most 0.65 times the extremal spin. The other black hole spin was not very well constrained. It could be as big as almost 0.93. You can parameterize the spin in various ways. Here we see that one particular, the aligned spin component is very well constrained, while the in-plane spin is not constrained at all. We cannot make a statement about the in-plane spin. It could be anywhere. It could be anything between 0 and 1, almost anything. However, although we cannot estimate the spin angular momentum of the initial black holes, we can estimate to a very good accuracy the spin angular momentum of the final black hole. I'd like to emphasize, So this measurement comes from the ICTS group, and I'd like to emphasize that this is one of the first accurate measurements of the spin angular momentum of a rotating black hole. With electromagnetic observations, you cannot measure black hole spins this accurately, with this accuracy. Here is the mass of the final black hole, and that is estimated to be around 62 solar masses. If you remember the initial masses and you add them up, then you would get 65. That means the difference between them is 3 solar masses. That means the total amount of energy that's radiated in gravitational waves is 3 times the entire mass of the sun, all converted into energy. And all this happens in a fraction of a second around the merger. This implies a peak luminosity of 3.6 into 10 to the 49 watts. Again, the ICTS group had an important contribution to this number. And this is probably the most luminous object that we have seen. The brightest electromagnetic object that we have seen, the brightest of the GRBs that we have spotted is about 100 times dimmer than this value. With this, I'd like to hand over the floor to Abhirup, who is going to talk about tests of general relativity with this observation.
Thank you, Archishman. Do we have any questions on this part before we move to Abhirup's talk? Okay, Abhirup, up to you.
Hello? Hello, can you hear me? So Archishman mentioned that a large part of his talk was covered by Rajesh and Ajith in the morning. Almost my entire talk was covered by Arun in the morning, so this will be a really short talk. And so as Archishman mentioned, that we can test the underlying theory of gravity with this observation, and that is because the interaction between gravitational wave science and the underlying theory of gravity is a two-way street, in which general relativity is one of the most important dependencies for the detection paper and all the companion papers. And that would again beg to ask the question that if we already have a detection, why do we need to again show that GR was correct? And that was kind of mentioned by Bala, that there are various relativistic theories of gravity that admit gravitational waves, and just because a GR template was successful in the detection of this binary black hole merger, still steps have to be taken to confirm that this merger indeed is consistent with other predictions of GR. And certain tests of gravity were certain tests were performed to show whether that was a right statement to make. So the first test was a consistency test, which showed that the mass and the spin of the final remnant black hole, whether the estimates obtained from different parts of the waveform were consistent with one another. And in that we showed that there were no evidence of discrepancies with the predictions of GR. This was a test that was kind of born and bred in ICTS, and with contributions from Archishman, Nathan, Chandra, Ajith, and myself. The other tests that were performed on this include a residuals test, which essentially means that in the stretch of data that we have, if we subtract out the best fit waveform, then all that we are supposed to be left with is the observational noise. And you heard from Sudarshan's talk that we have a pretty good handle of how that the detector noise is supposed to look. So this was a representation of the best fit waveform that was then subtracted out from the data, and this was shown in a slide by Chandra. What you were left with was the observational noise, and that was in very good agreement. Another test that was referred to by Arun was the constraining of the parameterized deformations, in which you can expand out the waveform in a Taylor-like expression and then constrain the coefficients of this expression. GR gives you particular predictions of what these coefficient values should be, and we show that within statistical uncertainties, they are extremely consistent with what numerical relativity predicts. Not only that, we also are able to provide much stronger bounds on the corresponding theoretical values as provided by binary pulsar observations. So as Arun mentioned, so the blue triangles are the observations from binary pulsar measurements, and the yellow boxes are the ones from this event. And the y-axis is actually a log scale, which shows there was an order of magnitude improvement in the constraints as provided by this event. A huge subgroup in LIGO called the testing GR subgroup was part of testing this, which includes the Iyer Trivandrum group, and also Anuradha Samajdar, who is sitting in the audience. There she is. So, to end up, there were two more tests that were performed. The first, obviously, has a huge contribution from Arun, and which was to provide bounds on the mass of graviton. And although a fully consistent massive theory of graviton doesn't exist yet, but we are able to put constraints of what that mass can be by constraining the corresponding Compton wavelength for the graviton. And finally, there was a consistency check of the least time quasi-normal mode in the data. So just after merger, the black hole goes through this period of instability, where it shakes off its asymmetries by irradiating in sinusoidally damped gravitational wave radiation, and it's possible to get the put constraints on the decay time, and this was found to be extremely consistent with the predictions by GR. So I don't have a summary slide, but to summarize the entire last 5 slides, within the scope of the tests that were performed, we have no discrepancies. We can report no deviations from our theory of gravity, like general relativity. That's Einstein's general relativity. Thank you.
Thank you very much. Virup, any questions on this part? Oh, yes.
I'm sorry?
No.
Is it possible to bound the charge on the black hole using these observations?
I don't think so, no.
I mean, I'm
No.
assuming it's close to zero.
Well, all the tests assumes zero charge black holes.
So, when we say that, so we are testing GR, so are we just testing perturbative GR or strong field GR? So how to make those distinctions? And
so we are testing strong field GR because just before the merger, the two black holes have a velocity of around half the speed of light. So
how much confidence do we have in the strong field limit, and do we distinguish between these two regimes and have different parameter fittings or whatever? Or we have same kind of confidence for strong field GR and perturbative GR?
So, Pallab, all these tests are null tests, basically. That basically all our models are, all of the models are GR models, and ask the question whether the data is consistent with GR. But these models are include the full non-linearities GR, and basically produced by combining perturbative calculations when they are valid with the full GR simulations.
out the initial you separate out the parameters characterizing departure in the initial part of the waveform and parameters that characterize departure in the later part of the waveform, and you can independently lay constraints on the departures in the inspiral part and departures in the later merger part.
Maybe if I can just ask a sort of subset of that question, which is, if we are in just the initial in-spiral phase and we are testing the post-Newtonian approximation, now there, I don't know much about the approximation, but it's a order-by-order expansion, and there presumably at each order, GR gives us some terms, but you know, you could just parameterize in general terms at that order in a more general way. So in that sense, at each order you could test perhaps.
That's precisely
that's what you did.
That's what you did. The test that Arun mentioned, essentially it's developed by people like Arun, Bala, Satyaprakash, and Chandra.
So this is actually providing constraints at each PN order.
This is the deviations, constraints on the deviations of the post-Newtonian coefficients as predicted by.
Okay, so it's still a null, but you do it order by order.
Yes.
Okay, thank you.
Okay, thank you very much. It's next is.
I just want to make one statement. Yeah, no, it's interesting that when this test was first proposed, people didn't take it seriously. They said, you know, all kinds of concerns. But the moment there was an observation, everybody wanted to use this particular test. So what was amazing to us is all the ideas which we have been sort of working on, which we thought were all, you know, just sort of first, you know, off principle kind of things, really were used and validated in the discovery. That was a big surprise because of the fact that the signal to noise ratio was reasonably high, and therefore many things which were proposed could be tested. But when we proposed it, everybody was quite cynical. But then, you know, the cynics came on board the moment the event was discovered.
Yeah. Excuse me, one more question. So there are many theories of gravity. So have you checked how many theories actually predict the same thing, or?
No, we haven't actually. So this is a null test where the null hypothesis is GR is correct, or whether GR can be ruled out to particular confidence level. But what it ruled out to is another question.
Any other questions? Okay, next is Nathan, who will talk about the neutrino follow-up of the event.
Yes, I'll actually talk about the generic multi-messenger follow-up, so a bit about the electromagnetic stuff as well. So I'll both give an overview of the EM follow-up observations, for which the companion paper is still in preparation with the astronomers, and then also the high-energy neutrino follow-up, which has already appeared in full. So, sorry, I must not have my phone in my pocket. So first, why do you do these multi-messenger observations? Well, we know multi-wavelength observations are very powerful in telling us a lot about sources. So here's a view of these sky and galactic coordinates, radio, optical, and gamma. You can see that there's a nice into the galactic plane there. Of course, now we've moved on from just looking at the whole electromagnetic wavelength to looking at different multi-messenger observations, both with neutrinos and God's waves, and now gravitational waves. The whole idea of multi-messenger observations is that we have not just photons to observe the waves these universe with, but also be able to observe the universe with basically the three fundamental forces, so both gravity, gravitational waves, strong nuclear cosmic waves, and weak neutrinos. So we typically expect if you have coincidences of neutron stars with other neutron stars with black holes, that you will see copious amounts of radiation, not just gravitational waves, but also photons and neutrinos, for instance, the ejecta, if you disrupt the neutron star. So for this reason, LIGO has implemented understanding with both electromagnetic and neutrinos trying to share triggers as they see. So for the first observing one, 01, there were 62 electromagnetic teams and 2 neutrino teams for which triggers were shared. So first look at the electromagnetic follow-up. So the idea was to share triggers that had a false alarm rate of less than 1 per month, just to have things that people look at in the sky, even if you don't believe they're all good, and they could be communicated to the electromagnetic and neutrino partners via GCN circuits. Actually, the neutrino partners, since they take data pretty much for the entire sky, they don't have to get them in real time. Electromagnetic observers need a point that telescopes the most part, so they need to keep it as soon as possible, except for radio, where these things will last a long time. So now, of course, we know that G25914 was a very black hole, as Arun told us about nicely, but so we don't expect to have any observable electromagnetic or neutrino emission, but electromagnetic observers did not know at the time, so there's actually quite a big follow-up campaign. So you'll note that here is a picture of the sky map you've seen several times before, but here it's on the sky. So you actually see that the large molecular cloud, or the companion galaxies to the Milky Way, is actually quite consistent with it. So electromagnetic observers looked for things there, thinking that because it was detected by burst search, perhaps it was a supernova. Of course, we don't know it's not, but this was still people were thinking up. They thought it was possibly nearby. So in fact, the source was followed by 21 teams using both ground and space rate instruments that across pretty much the entire electromagnetic spectrum from radio all the way up to gamma waves. So the results, first note that there was a set of sky maps that were released to the astronomers. First, these continuous wave bursts at LIB pipeline that Chandra told us about gave the initial ones that got sent out. Then there were some other ones intermediate. Then the final low influence one using these coherent techniques that Arun told us about is the one that actually you can see here in dark green. So there was some difference, but the general ring due to the time delay between two detectors is of course the same for all of them. So as I said before, the whole campaign is going to be summarized in a paper that's currently in the last stages of preparation, should appear early next week. But two of the observatories actually submitted their results already. One to the archive, one just released. They have public data, but have to submit immediately to a voting scoop. So the SWIFT and the Fermi Gamma Wave Burst Monitor teams have put papers out. So SWIFT did not detect the counterpart, as you would expect, given a binary black hole motor. They also had satellite in a good position at the time, so their wide field instrument was not pointing in the right direction. Then they followed up later, 2 days afterwards, and they received the trigger from LIGO. It was delayed a bit due to the fact that it was early on and it was not set up. Ideally, they will go out as soon as possible. They were focusing on nearby galaxies, not things that you would expect to see them. On the other hand, the Fermi Gamma Wave Burst Monitor used archival data to look at this. They look at the entire sky all the time. They actually do find something coincident. It is probably not actual counterpart. It would be surprising if it was, but of course they followed it very carefully. The data analysis is not yet reviewed from the gravitational wave side, though. So going to the neutrino side, again, they look at their archival data, and both with IceCube, with the South Pole, and Antares, the Mediterranean Sea, they both will Cherenkov detectors using either ice or water to look at the muon, and for instance, if you have muon and neutrino produced by charge current interactions, with the neutrino interacts with the ice. And IceCube detected 3 roughly tera-electron volt neutrinos in the 1,000-second synchrotron material diffusion 914. You can see they're here. Here is the sky map. The biggest one here is actually the 99% concentration, even lower than 90% in previously. So none of these are coincident with it. In fact, they're all the same as the background. So this is just what you would expect from atmospheric neutrinos from cosmic rays. Antares actually did not detect neutrinos in this period. So you can convert this with some assumptions on the spectrum into a bound on the energy rate of neutrinos. It's about 100 to 1 solar mass, depending on where the source was actually in the sky, because it's quite a large region. And the detectors have a variance in sensitivity of the sky. Looking ahead, though, if there's actually been something that we expect to emit electromagnetic radiation, something with a neutron cell in it, then this large moving campaign with 21 people looking at it electromagnetic alone would provide the first constraints on these various emission mechanisms, like kilonovae, for instance. Also note that after 4 gravitational wave detections have been published about, these nodes will go out not just to a private list, but actually to the public in as promptly as possible. So with that, I will now turn you over to Arun, who will tell you about how you can convert all of these sorts of things we've heard about previously into a complete picture of the source from the astrophysical point of view.
Thank you, Nathan. We have time for a question or two if there are any burning questions. If not,
Hello, so can I ask a question?
Yeah.
So if there are collision of two neutron stars, we are going to see that in ice cube, right?
I think it is.
Have you already seen any such collisions?
They only if they occur extremely close by. Neutrino fluxes are not very large. So just like you won't see supernovae over the entire observable universe, you won't see neutrinos from neutron collisions except in maybe, I think, tens of megaparsecs at most. And so these are not very many sources nearby. We can see them much further in gradual waves.
So I gather you didn't see anything exciting in neutrinos for this event, but let's say the gravity waves that originated in a supernova explosion, is there a characteristic in the neutrino signal as opposed to gravity wave signal that tells us it could be a supernova? That is there a time delay or something characteristic when you combine the two signals that could telltale by? Yeah, so you see the neutrinos and then you see the gravity waves, and do you learn more that way which could help you pinpoint that it was, say, a supernova event or of some particular type?
Absolutely. So you mentioned the time delay. So the neutrinos even are delayed slightly coming out compared to the gradual waves due to the interactions with the very dense matter. So, of course, this is something where these unmodeled burst searches are in the element. So there are many people who do numerical simulations of gradual waves from supernova explosions, but they produce many, many different waveforms. So you would have to actually try to reconstruct the waveform, which we all believe we've been able to do for GO5914, and then be able to compare this with the simulations you've done, and then, of course, you'll get much more from the neutrino side as well, seen in, for instance, just the flux, and also I think even the flavor composition. But I think here the trigger would likely go the other way. You'll see a large burst of neutrinos from a given direction, and then you will be able to trigger and look in your gradual wave data. Do you see something and look very deeply? Because you emit the most energy in neutrinos with supernovas.
The only issue is that we are, as gravitational waves, we are only sensitive to galactic supernova.
Unless you have some sort of extremely exotic thing going on in
nearby galaxies, yeah. So the rates are very, very important.
Thank you.
If there are no further questions, the last talk by Arun Mukherjee.
Good afternoon, everybody. I would first like to thank all the speakers who have given a very nice introduction and have done a very thorough job. Have done a very thorough job of describing this particular discovery, and also they have pointed out a number of tests and parameters here. So. Just before the lunch, I would like to invite you all to take a quick walk with me in the regime of astrophysics and what we think could have happened before this particular, astrophysically, what could have happened that has given rise to this particular event that we see in LIGO detectors. So plan of the talk very quickly. Formation of stellar mass black hole in our universe. We would like to say how these typical stellar mass black holes are formed. We'll also then have a quick look at the formation and evolution scenario of binary black holes in nature, and then how they end up in spiraling and merging, producing a gravitational wave signature, a very clear, distinct one seen very recently by LIGO, and in future predicting what we think that how many such events can be seen in upcoming LIGO science runs. So let's begin. So this is a picture, actually it's an astronomical picture of molecular clouds, and from there the journey of this stellar evolution cycle begins. So some of the stars are really small and very much like our sun, and they go to the red giant phase after burning out their hydrogen fuel and goes to the planetary nebula. It's kind of an explosion that leads to a white dwarf that lives sufficiently long and enough time, which is considerably larger than the age of our universe, eventually radiates all its emission and will become a black dwarf. However, if the star is really, really large, massive one, then it goes a red supergiant. And when it burns out all its fuel, nuclear fuel, then it goes a supernova. This is a picture of Crab Nebula. It's a supernova remnant that would have happened several centuries ago. And depending on the mass of the core of the burnt out fuel, it can become a neutron star. Or if it is even more massive, nothing can withstand, and it falls due to the collapse of its own gravity and forms a black hole. And this is an artist's impression of a black hole around an accretion disk here and a jet here. Of course, we can't see the black holes electromagnetically or in other way. Now let's look how we can get a double black hole system in our nature. Very similar to the previous slide, we start with two massive stars, essentially OB type. And in the left side, I indicate the typical time scale that is involved during this each phase of their entire lifespan. As it happens, first the more massive stars burns out its fuel, it fills the Rousseau overflow happens, there is some amount of mass transfer through this particular point called L1 point, first Lagrangian point. There is some amount of mass loss also happens, and then it's left with a helium-rich OB companion. And then from there you have to come this side, somehow the arrow is missing. And what happens is that once the primary burns out its fuel, as I shown earlier, it goes a supernova. The lesser massive star is still alive, it's still a main sequence star, and during its lifespan of its evolution, it again fills the Rousseau and loses some amount of mass and also transfers certain amount, a small fraction of mass perhaps, and it enters in a phase, it's called common envelope, where both the two stars, like the secondary star and the black hole, are inside the common shared envelope of the expanded material of the secondary star itself. Then again, secondary star also runs out its fuel. It goes another supernova, and depending on the supernova kick, the black hole system can get disrupted, and they become two separate individual black holes, or it can so happen they are so tightly bound, or it can once in a while even assist to keep the two systems come closer with a suitable direction of the kick velocity, and they becomes tightly bound and starts orbiting towards each other. And that leads to the point where we have two black holes. This is a particular picture, snapshot, from which we start our journey of the in-spiral merger ring down part. Here is a video from the SXX group and done by Harold Pfeiffer from CETA. I'll show you this video. Bottom you can see the gravitational wave signature. These are the apparent horizon of two black holes going around each other. In this color code, this is the scalar curvature. And this field line shows the local direction of field of gravity. This is the exact numerical solution of Einstein field equation. It forms a common apparent horizon, and then it settles down. It's a wonderful job by SXX group. You can see the gravitational wave propagating out from this merging event. And that is, the whole credit comes here, sure, I will love to play it. We can see the gravitational wave signature here, and that is what registered in LIGO detectors, both in Hanford and Livingston. Artificially slowed down, you can see the time lapse in real time. Common apparent horizon forms, scalar curvature changes its signal, settles down after merger. It's wonderful. The gravitational wave is carried away from this source. The credit goes here. And in my final slide, I will very briefly mention that this is just the beginning and many more to follow. And in the left panel, you can see the rate at which LIGO detector accumulated the data of that accumulated the total amount of surveyed time volume of the local nearby galaxies that could have potentially give rise to this type of event. And in the right panel, in the right side of the figure, we can show that the expected number of highly significant events that could have occurred during, that is likely to occur during the second science run of LIGO detector, advanced LIGO detector, and third science run of advanced LIGO detector. And the probability that we observe more than one event in the blue curve and more than 5 events, or at least 5 events in the green curve, and 10 events in the red curve, and perhaps 35 events in the purple curve in this particular diagram. And the vertical lines indicate how much time volume we will have covered as compared to the one that we have observed here, and that is shown from beginning to the end of second observation run, and beginning to end of the third observation run. And with the final statement, I would like to finish my talk and the whole session, is that it's been a very long time, and this experiment has been done by so many people over the decades. It's certainly the end of the quest for gravitational wave direct detection, but this gives a great hope of opening up a new era, a dawn of gravitational wave astronomy, with so many events to follow. Thank you very much.
There's a question.
Can I ask a question?
Sure, please.
Can I? So these black holes which merged are around 30 solar masses, 40 solar masses. Aren't they too heavy to be produced by supernova remnant?
So, not really. Depending on, there are certain type of exotic supernova engine which says that it might be difficult, but most of the canonical picture says that it's very much possible to produce stellar mass black hole as high as say 30, 40, or maybe much more, like 80 solar mass. That's not very like a difficult thing to produce. What is very difficult is that to observe such massive black holes in nearby universe where metallicity is sufficiently high, that might cause some amount of problem, because the main sequence star may lose lot of mass due to the wind from very massive, very large amount of metallicity environment. However, it might have happened that this double black hole system had formed sufficiently early in the universe, but slowly spiraled down and merged now. In that case, it's perfectly fine.
Thanks, Arun. I just wanted to, make one statement, because it's not emphasized enough. We talked about some work with, which I had at RRI, and also Sanjeev Dhurandar's work. We also had long collaborations with another person who was a postdoc in Sanjeev's group, that is Satyaprakash. Satyaprakash, my group, many of these tests which we talked about, the use of parameter estimation to how accurately you can do it by using post-Newtonian waveforms, how to test GR. All those work was done jointly. Also my work, for example, in terms of using Pade approximants, many things were done jointly with Satyaprakash. The LIGO India project, we had to very quickly come up with the advantage of doing localizations by the LIGO India detector, and Satyaprakash was one of the people who defended it in the NSF reviews. So I just wanted to acknowledge a close colleague, Satyaprakash.
Thanks, Bala.
I've got a quick question, more like a request. Can I get a copy of that movie?
That is publicly available.
Oh.
And I can point you to the better, even high resolution. It's a 4K rendering of this thing. And of course, the slide is here. So, and I can personally mail you. And,
and we'll also put up the links of all these talks, and I think the videos and everything should be coming on very soon. So this will be all publicly there right away. Thank you. Yeah. Tarun?
I just wanted to point out that at the press release of IndIGO, we did make available a lot of media material. Okay. I think you should look at the link. It is gw.iucaa.in/press or /G, just one letter. And that has quite a few new things that our students have put together, and also from available material and on their own.
So if we just Google IUCAA gravitational waves.
Just gw.iucaa.in. I don't know whether, yeah, maybe it will show up. I don't know.
To your main event page, and probably it's linked from there also. Yeah.
Just one comment, since Satyaprakash was mentioned, I want to take this opportunity also to say that in setting up the Astrophysical Relativity Group in ICTS, Bala, Tarun and Satyaprakash played a very, very important role. I just wanted to record that. Thank you. Thank you very much.
Yeah, Madhavan, you had a question.
People are making comments. I actually wanted to make this comment in Arun's talk about the Indian role. And this is to my understanding, you can correct me if I'm wrong, Bala, etc. In the PRL paper, as well as in the talk, at least I got the feeling that post-Newtonian methods for this particular observation were not that, they didn't play that much of a key role. And my understanding is, even in the paper, it's always referred to as numerical simulations everywhere. But the initial data for this numerical simulations has to come from these post-Newtonian calculations, and is my understanding. Is that correct or is that wrong? That's not. But I mean, I think post-Newtonian calculations have been crucial in what has gone on over here. And of course, Bala and his group and other people, I think, maybe you're too modest to say this. And I think their contribution, deserves even a sort of a higher profile than what has been given to it in the PRL. That is my understanding. You can please
I fully agree. And in fact, I think Arun also was too modest to say that in his talk. But it's really important that, to note that essentially all the waveform templates that are used to detect a signal as well as to estimate parameters, basically the fundamental input is the calculation of this post-Newtonian waveform, which came from Bala and his collaborators, with a major contribution from several of his students and postdocs, including Arun. So it's very, very important to recognize that.
Yeah, thank you. I think it was very nice to have all these comments. I wanted to close the session with saying that I really appreciated what the younger people did, the talks all of you gave. It was so beautifully, thematically organized. It took us through so many different facets of the discovery. I think it was a very well done job, I think. So congratulations to all of you. I think the morning session we close now. We'll have lunch. Please do come afterwards. We'll have a talk by Tarun as well as by Professor Vishveshwara, whose work all of you have heard about now. So we'll have these talks right after lunch. So it'll be a short afternoon session. Have your lunch. Please come back quickly. We are running a little late, so